Samarth, thank you for being here. He's our next speaker. But actually, even though I had you sit, let's show your badge to the audience first. Yeah. Can you put the couch camera? Yeah. Okay. You can kind of see it. It's not perfect, but he programmed basically. Well, you know what? Hill's gonna tell you. So, what did you put on your badge?
Yeah. So, okay.
We're sitting back.
I design and make games, and I'm very bad at marketing and advertising. So I thought today let me be a walking billboard for my released game. So yeah, it's a very simple vector-based animation with like small movements. Yeah.
Yeah, that's awesome. So please give it up for Samarth. Thank you. Okay, so we're on to the top.
Yeah. So I guess I want to ask you all a question when we start. When was the last time you had this feeling? My goodness, what an idea. Why didn't I think of that? And for me, a lot of times this question is a retrospective question. Why didn't I think of that earlier? Why did I spend the last 2.5 months working on the system, finding all the edge cases, solving all those edge cases, creating more bugs, creating more errors, when now this new idea that I have solves everything in one shot, right? So I think those kinds of ideas, I call them insight. So that's the title of the talk. Step back, dive deep, finding insight through breadth and depth. It's a very long title, but we'll get through it slowly, right? So yeah, a bit about me. My name is Samarth. You can call me Sam. I'm from Bangalore in India. I think I like being curious, and it's helped me a lot. I write software, I make games, and I'm very excited to be here in Milan with all you fine folks. So yeah, this is my advertisement again. I made this game. It's called Konkan Coast Pirate Solutions. It's a cozy puzzle game about helping pirate ships do pirate things. It released last year in March on Steam. It's written in Zig, and it taught me a lot, right? Specifically, it's a puzzle game, and every good puzzle teaches you something new about the system or the game or the world. And the experience of playing a puzzle game should be all about this insight, right? That every puzzle teaches you something new, teaches you a way to reframe everything that you've seen up till now. And I think that's something very beautiful. And that's why I'm trying to work on my craft and work on more of these things. So specifically, it also taught me a lot more about insight. So to give some more examples about what I think is insight, I have two problems. The first one is about increasing speed of data read from a disk, which means that someone hands you a hard disk and says, I need to read data faster off of this disk, right? What is one way you can solve that problem? And the second is calculating the inverse square root. This was a big problem maybe 30 years ago, where people were not able to use 3D graphics because this specific calculation was very slow. So yeah, the first question, reading data from disk. I think there's a better explanation than I can give, so let's just go through that. Yeah, so yeah, compare a point on the label with a point on the edge, and you can, I guess, read it. And yeah, my reaction. So this is, of course, playing a record on a vinyl disc, but the same thing can also be said about reading data from a disk, right? When you look at a point on the outer edge, for the same amount of rotation, you can store more data because it covers a greater distance. So, I mean, this is like a known problem. It's called zone bit recording. And it's the same idea that for a given speed of rotation of disk, areas on the outer edge will travel faster. And that's why you can store more data and read it faster when it's closer to the edge as compared to towards the center. And this is also why disk reads can become slow once the disk is full, because traditionally all data starts being stored from the outside, and the closer it comes to the center, the slower it is because of this like limit of physics. And that's why it feels like it's slow, even though it's not necessarily degradation of hardware. It's just this phenomenon. So I guess there's like a couple of points of insight here. So in this case, rather than thinking of memory as abstract or a hard drive as an abstract system, you try to go outside of that and understand exactly how data is actually stored. And we often talk about the limits of physics, but in this case, we are like empowered by the features of physics, right? There's something fundamental about how circles rotate that allows us to, and if we understand that and use it correctly, we can kind of exploit this feature and have faster data read. So the next problem to discuss is inverse square root. I think it's a fairly famous solution that a lot of at least game devs talk about in very high regard. So, this is what you're trying to calculate. The inverse square root of x is 1 divided by the square root of x, so inverse square root. It's useful in 3D graphics for lighting calculations specifically. It's expensive to calculate, relatively speaking, because it has a square root and a divide, both of which are expensive operations. And it was famously solved in Quake 3, which of course means that in the game called Quake 3, they had a solution to this, which was fast enough that it could be used in the game and not affect everything else, but give you big benefits. So this is the code. This is the code. So you start off with naming some variables, some ints and floats, and of course the 3 halves, which is 1.5, which if my math is right, that is 3 halves. So you start off with a couple of calculations. You half something, you set something else, and then you do this operation, which is you are calculating. It's some kind of pointer change. Like maybe the comment will help us. Okay, it's an evil floating point bit level hacking. Okay, it's not me that. It's not just that I found it hard to understand it. It is like evil. So the next step, of course, is this. So maybe the comment can help us out. Yeah, I think that's one of the more famous comments I've heard of. Then the next step, of course, is again something similar to the first, where you're doing something more evil, and then something more. So this is the code, and we know that it gives you the inverse square root of a number. But I think how much ever you read this code and try to understand it, you're not going to understand how it works, right? Because you're lacking some level of insight, which is what allows this to happen, right? I don't see any divide. I don't see any square root. So how is this being calculated, right? So for that, I think we need to go through some other topics before we can come back to this. So the first thing is, how is floating point implemented, right? So floating point is designed to store real numbers, which are like not integer. So like 1.7, 3.14, or any other numbers that are not whole. It's very performant at the hardware level because a lot of optimization has gone into making sure that this specific floating point implementation runs fast across all hardware. And it uses the principle of exponents, which is very basically you have, this is how the floating 32-bit floating point is stored, roughly speaking. There's 1 bit for the sign, there's 8 bits for the exponent, and 23 bits for the mantissa. So suppose you want to say I have the number 217. Rather than storing it as 217, I'll say 2.17 into 10 to the power of 2. So that's very basically how floating point is stored here. So the next thing is that calculating in exponents. So specifically for our problem, if I have the number n that I want to find the inverse square root of, if I can express it in the form x to the power of y, then the inverse square root becomes x to the power of y minus y into minus half. So basically we have converted a square root and a divide into a multiply. But of course it means that we need to be able to convert this n into the form of x to the power of y. And also this specific multiplication, y to the y into minus half, it could also be expressed as some bit shifts, which is an even more efficient way to solve the problem. Finally, when we talk about how data is stored and how you can do some really fancy things with pointers. So one insight is that all data is ones and zeros. Everything in the computer, whether it's a number, a floating point, or an image, it's always ones and zeros. So if we interpret float data as an integer, we can access the mantissa and the exponent, which was previously called x and y, and now we can operate on that. So even though the floating bit, the 32-bit floating point is stored in this manner, if we try to like hack around it, we can directly be exposed to this exponent and this mantissa. And as we saw before, if we have this exponent, then we can very quickly do the calculation that we want. So again, coming back to the code, so this evil floating point bit level hack is this, right? So y was a float and I is an integer. So what we've done is we've converted, we are reading floating point data as an integer. So if I try to print I, it will give me a number that makes no sense, but I can then do this bit shift, and this constant is something more to do with the floating point implementation. And when I convert it back into y, I get something very close to the inverse square root, and this is just a numerical method to get closer to the answer, right? So to go from the code to understanding the code, we needed, again, like a few points of insight based on where your strengths are. So we need to understand how a floating point is implemented under the hood. We need to understand that expressing the same problem in terms of exponents makes it easier to solve, and C will like do whatever you want it to do. So we can do all of this like weird hacky things around bit manipulation and things, which means that the problem is now can be solved efficiently with the goal of having better graphics or more efficient software, more powerful software. So these were the two problems we discussed. The first is increasing the speed of data read from disk, which feels like we stepped back, we looked at the physics of things, and then we got some insight that we can now solve the problem better. And the second one is calculating inverse square root, which we dove deep into the implementation of floating points, and then understanding that, we were able to solve the problem better, right? So yeah, that's it was insight that allowed us to do that. So in my opinion, this insight is valuable. If I just give you those problems without any explanation, you might spend a long time and not be able to implement any meaningful solution. But if that insight is given to you as well, even though it might not be straightforward to implement, you know the steps to implement, right? So implementation becomes easy once you know what you're actually trying to do, as opposed to trying to find this insight. That's the hard part. So yeah, that's the title of the talk, how stepping back and diving deep allows you to find more insight. Though this was the title I submitted back when I didn't really understand this better. If I did, I would probably call it just insight with some punchy tagline, which I've not had time to come up with yet. So that's basically what this talk is about. It's about understanding this power of this idea of insight, which is we can go more into. So I'm mostly a game developer. So I want to explain some points that I found in the graphics pipeline, right? Specifically, which is how do you draw things on screen. So very basically, you start off with CPU and you read some data. This will be like a model where the position of each vertex of a cube, for example, you'll read that and you'll pass that data to the GPU along with some other things. And on the GPU, there are two major steps. The first is a vertex shader, which converts those 3D world positions into positions on the screen, and the fragment shader, which decides the color of each pixel. So again, in a diagram, you read some data and some 3D objects, and you have a game engine which sends data to your GPU, to the vertex shader, fragment shader, and finally to the display, right? So the first thing on the CPU, we have, for each vertex, we have some data, the position, the texture that is mapped to that point, the normal, the direction that it's facing in, some other stuff. Then you have a texture, which this texture coordinate is referencing. Then you have some data about the world, like where is the camera, where are the different lights, what are the different graphic settings, and other things which are useful to, which are going to be useful to render things on the screen. So all of this data is then sent to the GPU. So on the GPU, we have a vertex shader, which is just a code that runs on the GPU. So for each vertex, we can convert the 3D position to a 2D position on display. So again, you have a cube floating in the air, and you need to understand exactly where each point of that cube is, which pixel on the screen it's going to be plotted to. So it's based on the orientation of the object, camera, and some other camera characteristics. Then within the GPU, somewhere you say that which 3 vertices make up a triangle, and then that's passed to the fragment shader. So the fragment shader code runs for each pixel within that triangle that we just passed in, and it would generally query the texture for which color it should be. It will update the color based on lighting, so based on the color of the light, and based on the direction that that face is facing. So if it's facing towards the light, it will be more affected. If it's facing away, it will be less affected by the light. Then there's some internals that make sure that things in front are drawn in front. And then finally you have this cube, right? So for example, this face is facing towards the light. So even though these 2 blues are the same in the texture, this one is lighter and this one is darker because this one is in shadow, and this face is facing towards the light. So this was what I initially learned, and I was trying to then do more creative things with this pipeline. So the first thing I learned is that textures don't have to be color. So you can store any information for each pixel. So previously I was storing that this specific point on the cube has blue, and I'll store that blue value in the texture. But I can store any other information as well, right? So for example, there's this concept called normal maps, where rather than storing the color, you store with the orientation of that face. So this is an example of a normal map. So you can see that it's mostly purple, but no, the image will not actually be purple. But if you look at the corners, you can see that this corner is more blue and this is more like pink magenta, which means that these 2 points on the surface are facing in different directions, so they'll interact differently with the light. So here you see the same image with normal mapping and without normal mapping. So once we add this additional data per pixel of which direction the pointer on that wall is facing, we get this seemingly 3D thing for very cheap. Rather than having to store hundreds of triangles and show them, we can just add this normal map data and have a better understanding of the 3D orientation of the object or the texture of the object. So previously we said that textures should be in the fragment shader, but there's no reason they can't be in the vertex shader as well, right? So for example, we can say that we have the displacement of each point, and that's stored in a displacement map. So for example, you have a tree here, and the redder the pixel is, the higher up it is. So in the vertex shader, you can apply displacement, which says that the higher points in the tree move more in the wind than the lower points, because this is grounded. Similarly, the farther you go along the branch, the greener it gets, and at the edges, you have more blue. So using this simple data, you can, in the vertex shader, do a lot of animation because you have more than one, you have more than a single transformation for each point. You can also add this data. So the next thing is texture can be more than a pixel mapping, which means that previously each point on the model had queried the texture for one point. But now if we, for example, we can have this animation where each pixel has an entire column of values that it can query, which means that we can bake in an animation into this texture, which again, like, makes no sense as a texture alone. If you look at it, you have no idea what it could be. But once it's mapped onto the object and based on time you query different rows, you can see that the colors will give you a different motion. So this whole animation, which could have otherwise been a very expensive process, we have to calculate the transformation of each bone and each face based on the movement of each bone in the skeleton, now all gets packed into this one simple vertex texture, and thus you have like very efficient way to express animation data without having to do too many calculations at runtime. And finally, the output of the graphics pipeline does not have to be on the monitor, which means that a GPU is just an embarrassingly parallel computer. It's just very SIMD. So, and multiplication, whether you do it for graphics or whether you do it for machine learning or whether you do it for accounting, multiplication is still multiplication. So everything is ones and zeros. And if you understand that the GPU is just another kind of computer which is better at some types of calculation, you can get out an image and then read that data and understand it the way you want. Even though it may not make sense as an image or as a PNG, you can then draw the data from each bit and then understand the multiplication that you were trying to do. So again, like these are some GPU insights. The texture doesn't have to be color. It can store any data. Any data can be extracted from textures, and that all compute is the same. So going through this, I started to understand the difference between an abstraction and a model. So I think we're all very aware of what is an abstraction. It's a technical concept where operation is streamlined, and that streamlining of the operation might restrain capability. So for example, if you have a file system abstraction, it might mean that it works differently on Linux and Mac and Windows. And it might mean that Linux has some specific capability that the other OSs don't have. But because of this abstraction, you cannot express your exact thing on Linux while using that abstraction. Secondly, there's a model, which is like a mental concept. The way we think about the system and the way we think about a system may prevent us from using all of its capability. So for example, when it came to GPU, like the GPU is a graphics processing unit. Like it accepts textures. This gives us ideas of very visual things. And so it's very easy to get stuck into this idea that GPU is meant for graphics, even though all it is it's the computer. So even though the OpenGL or Vulkan does not limit us from doing random calculations for other purposes, it's just this mental model that I had created where it meant GPUs for graphics, therefore I should be using it for graphics, right? So so the insight for me going through this expansion of the graphics pipeline was mostly about breaking free from this model that graphics means I can only use it for graphics. So yeah, I mean, but models are useful. Just because we say everything on a computer is zeros and ones, it does not help us solve any problems. I can say that Romeo and Juliet in ASCII is zeros and ones, and the Zig compiler is zeros and ones. But that doesn't actually help anyone. So having this model of, okay, ASCII, these numbers map in this specific way has a lot of value. But also we need to analyze all of the models that we have in our code and in our systems and see if any of them are limiting us from the true capabilities that we would like to achieve. So now I really wanted to then go through each insight that I had and say whether that was from stepping back or diving deep. But the more I did that, the more I realized that that model maybe doesn't make sense. That I can say that I stepped back and then I realized that all data is zeros and ones, and so floating point I can manipulate. And similarly, I dived deeper and I looked at my exact hard drive and tried to understand what is this motor speed, and then I came through this conclusion. So I think that also taught me more about the nature of insight. That it's not as easy as saying stepping back or diving deep. So the way I would frame it is that insight allows us to reclassify the problem by breaking it down into simpler systems, and specifically into the correct set of simpler systems, right? In most cases, when we have a large system and we try to break it up into smaller systems, the issue happens when the breakup is incorrect or not ideal or doesn't express the thing that we want to express in the best possible way. So gaining insight is all about knowing as much about these different systems as we can. So once we either dive deeper into a problem, we can try to understand all of the things that build it up, and then see what is familiar to us in the same domain. Or you just randomly explore your curiosity and find things that then allow you to map them onto the problem that you're trying to solve, and try to do it that way, right? So I think especially curiosity is the most powerful thing in this, because a lot of curiosity comes from a subconscious level and we don't give it the kind of respect it deserves. That the subconscious can understand these ideas and map them very well, but we don't have the words to express it, and we don't have the way to express it, and therefore it generally comes out in the form of curiosity. When you're solving a problem and you're suddenly drawn to another domain entirely, it generally could be that subconsciously you've drawn a correlation between the two, and this is the only way that our subconscious can express that there is value to be gained from studying another domain. And I feel that following that curiosity has always allowed me to have better solutions to the problems, and how learning metallurgy or biology can really help you in tech and other fields, right? So I think that curiosity and the value of it is often understated, because as technical people, I always felt that logic is, and reason and words and explanations are the most important. But the deeper I go into this, the more I see that following random threads always leads you in good directions. So I want to talk about simple and complex. So I think that if there's one fundamental truth about the universe, it comes from this: simple systems interact to create emergent complexity. For example, molecules interact with each other to create the gas laws. Like, this idea of temperature comes from the number of times that a single molecule hits other molecules, which means that each molecule has a simple system that it follows, where it moves around and it hits other things. But when you take that in totality, all of the molecules in this room are hitting each other a lot. That's why it feels hotter. Whereas outside, that's happening less. So similarly, when you say the gas laws, that's how pressure, volume, and temperature react. And then that makes more sense. When you compress something, there are more interactions, and that creates this idea of temperature and pressure. All comes from this very simple, each molecule acting on its own, all combined then gives us these concepts. Similarly, each of our choices interact to create, like our economic choices, financial choices, all interact to create this whole system of economics. That if you look at the law of supply and demand, it all comes from us saying that something is cheaper so we can buy more, or vice versa. And finally, like, there are 4 fundamental forces, and there's this thing called mass and energy, and that gives us everything that we know, right? From universe to galaxies to planets to Zig conferences to software you can love, right? All of it comes from these very fundamental things that are all interacting at different levels and creating something that's way more than you can probably assume if you start off. And I think that the best solutions mimic this aspect of truth, that there's something about the universe that has a way to express complex things via interactions of simpler things. And I think the simple systems allow us to express that, right? So the best solutions are always, whether it's a code, whether it's a product, whether it's a system, by every metric, cost or ease of implementation or ease of expansion or ease of understanding, they all seem to strive towards this, that the best solutions feel like they are the simplest they can be, with the most interesting emergent reactions between them. And that's what creates things that are like beautiful. So that's what I feel, that insight allows us to reach one step closer to something that is true. And these solutions, they get better the simpler they become, because this is something about the universe as a whole. So sometimes I think about why I write code, and I feel like programming feels like the most direct way to observe and interact with something fundamental. That when you write code, you can really see and understand how these things interact with each other, how complexity comes from simplicity, how you take a bunch of simple things and throw them together, and it gives you more than you can ever imagine, right? There's this kind of magic about it that says that these simple things can really give us a lot more than we put in. And the beauty is in finding those simple things and re-expressing complex ideas in these simpler forms, and that will again give you even more. So I think that programming allows me to search for something deeper, something true, and something meaningful, because every day you come across these problems where or these scenarios where suddenly something clicks, something works, and like there's something like really magical about it. And I can't really put it in words, but maybe that's why I make games. But it's something very subtle and something very deep, but something very true. And I just love this. Right? I love being here. I love writing code. But most importantly, I love this feeling. My goodness, what an idea. Why didn't I think of that? That's all. Yeah. Thank you.
Thank you, Samarth. Thank you very much. That was probably the most wholesome talk in the whole conference, so that was great. Let's see if there are questions from the audience.
Hi. I was wondering, you were showing using a texture as a way to transmit and store animation keyframes.
Yeah.
I was wondering how, I guess how much more efficient that was from a like transmitting data perspective instead of using a buffer. Is it because it's compressed?
Specifically, wait, let's go to that. Specifically, the idea is that when you look at this model, it will have a lot of bones within it, and each of those bones will have to then be calculated as per the animation that through like curves and through endpoints or keyframes. And to do that for each model will be very expensive. Whereas if I have this one texture for every model, I can have thousands of these without any additional computation, because it all happens in the vertex shader, and I can all have them timed differently, or I can have like 5 textures for 5 different animations, and it's all like baked in. So that's the main idea, that if you have one thing, then maybe it's not a big thing. And also when you have one model that needs to move, then you might have other things that it interacts with. In all of those cases, this is not useful. This is generally useful for like crowd behavior or NPC behavior, which you're not going to interact with directly, but you're going to see in the background, but adds life to the world that you're trying to create.
Hi. So following up on the last question, the way all the data is stored in the image is, of course, well, not optimal, but it's still very, very efficient. So compared to like compute shaders that are only available in very few systems, very few platforms, would you recommend just using what we have and sticking with the texture, even if you want to have, I don't know, a non-deterministic sort of approximated simulation or something? Would it be, in your opinion, like a good way to go, or not?
So I think this is a special use case. So there's this game called Abzu, which has upwards of 100,000 fish on the screen at all times. So for a scenario like that, you need a cleverer solution than what is the standard, right? The standard is a standard for a reason. It's easy to work with across the stack. Like artists understand it, developers understand it, and engine understands it. But there are times when you need to break away from that because for some reason or the other, it's not ideal for the specific scenario. So in most cases, I would suggest stick with the known best state of the art, because that's generally enough for most scenarios. But there are times where you have to do other things to like extract every single ounce of energy that you can. Yes.
So mine is more of a comment on kind of the end of the talk where you said like, why do I program? Someone asked that question to me as well not too long ago, and my answer was, something along the lines of the rush when I'm debugging something and I find the solution to that bug. And I think you put into better words than me. It's because that gave me insight into the system and teach me something about it that I didn't know, and now I know, and that kind of adrenaline feels great. And I think that's why I program as well. So thank you so much for your talk. It was amazing.
Yeah, thank you. I think it's the same journey, right? You start off with the simple thing where there's an immediate feedback and allows you to really like engage with the thing. But over time, I felt that there's something deeper there as well. And I think this is my best effort at trying to explain that.
Hi, I really loved your talk. Very, very good. I was curious if during making your game there was any moments of having like deep insight or finding a truth that you really like resonated with you, made you feel like, oh, I love this.
I think like especially in puzzle games in that genre, every point is trying to express that, right? That every good puzzle is a way to express that. So I mean, I had hundreds, if not thousands of those, and I tried to make each of those into one puzzle, into one level, and only the ones that translated well are in the game. But at one point, all you're doing is exploring the system. You've made all of these rules, like I'd made all of these rules, and I was just throwing things at it to see what would happen. and there are so many magical things that happen because I've coded the whole thing myself. I know every line of code that's there, but still when something happens that I did not expect and things interact in magical ways, that gives you a rush. You sit down and you're like at the whim of the universe. Like, I don't know if I'm going to be able to find a good level today because it's not in my hands. Like, it's in the system, it's hidden somewhere deep in there, and I just have to try and find something. So it's both exhilarating and like terrifying.
Yeah, that sounds like a beautiful feeling. Thank you.
Okay, one last question.
Yeah.
Sure.
My question is, what is one of your favorite games and why?
I think there's this game called A Good Snowman is Hard to Build. That's my favorite mostly because it showed me how a simple system can have a lot of magic hidden within it. But also it showed me that a game is not like this magical thing or this extravagant thing. It's the game itself takes maybe 2 to 3 hours to play. And after finishing it, I felt that I think I can make games as well. Because every other game you play is all this like big AAA things which has hundreds of people and thousands of like millions of dollars put into it. And as an individual, I don't know how I can aspire to that. But this game specifically, it allowed me to think that, okay, I mean, I love that and I would love to make something like that. So I guess that would be my answer.
Yeah, great answer.
Okay, thank you. So can you give us precise instructions on how to get your game?
Yeah, so it's available on Steam. It's called Konkan Coast Pirate Solutions. If you search KCPS on Steam, you'll find it as well. Okay. Otherwise, I guess I can put up a link on the Discord.
That would be awesome.
There is, I have a couple of articles about it on zig.news. So, I mean, you might have to scroll a bit, but you can find it there as well. And if anybody would like a key, you can just DM me on Discord at ChappiBoy. And I'll share those. Like, I have a lot of them. So I feel free to reach out and I'll just send you a key across if you think it's something that interests you. And also one more thing, like the game is made for a slightly niche audience or a more experienced audience. So it's not for everyone. So I'll just put that disclaimer out there. It may or may not click for everybody because it was made with a specific audience in mind. But I would love if you guys would try it out and give it a shot. Just don't feel bad if it's not clicking.
Please give it up for Samarth. Okay, we are going on a lunch break, so let's put the stream on a lunch break and we're back at 2.